The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Welcome to 6172 Performance, what is it called? Performance Engineering of Software Systems, that's right. Good. This is a fun class, okay? It's all about going fast. Okay, we all like to go fast. Well, not all of us. But everybody in this class likes to go fast. Okay, otherwise you won't like the class very much. Okay, it's all about making stuff go fast. Okay, it's taught by, so a couple of just brief announcements. We're going to be videotaping for OpenCourseWare. Okay, so if you don't want to be videotaped, you should sit in a place where the camera won't catch you. Okay? Because we're in such a large classroom, I'd like everybody to sort of, every day without me having to draw. I'm not really an artist. My sister's an artist, actually. She's a painter. But me, that gene escaped me. It went that way and not this way. And so I don't want to have to draw that up again. So everybody try to confine yourself to this sort of quarter of the classroom, and that way it'll feel more like a size room that we ought to be in. Let me go to our course information sheet. Did everybody get a copy of the course information handout? Okay. So we're going to do the class, we're going to start at the beginning with the administrivia stuff. Okay, try to run through that as quickly as we can, and then my co-lecturer, Professor Saman Amarasinghe, if you can't pronounce it or spell his last name, you can just say Saman, okay, will give today's lecture. And we have 4 teaching assistants. Okay, so teaching assistants, please stand up. They are Josh, John, Reed, and Eric. Okay, and let me tell you, what they have done in the last few days to get us ready for this course is nothing short of superhuman. Okay, so you really need to accord them your respect, and they're going to really work hard to help you folks do well in this class. Okay, we have, I think, a pretty decent ratio. I think even with concerns about cutbacks, et cetera, to have 4 TAs for this is really good, and we need it because it's a software class, and software is, as you know, bugs can take an arbitrarily long time to find. We have 2, besides, you guys can sit, besides our teaching assistants, we have 2 support staff people helping us. Mary McDavitt, who works for Saman, and Marcia Davidson, who works for me. And they're generally pretty good about being able to track us down if we're in some far corner of the world or something. Our lectures are going to be held on Tuesdays and Thursdays in this room, 2:30 to 4 p.m. You should plan to attend regularly. We dispense all kinds of wonderful gems that you will miss if you think you're going to get it just from reading and even looking at videotapes or whatever. I'm not sure what our arrangement is going to be about having videos available. Okay, they're not going to be available, okay, except unless there's some really extenuating circumstance. You know, you have to go into a hospital to have your, your forebrain removed or something, and then you can, something serious, okay? All material in the lecture, even if it's delivered oral, is fair game for projects and quizzes. Okay, we will post the lecture slides, but they don't generally convey all of the information. And we're going to be video recorded, as I mentioned. If you don't want to appear, sit behind the camera, and you won't appear. We have no recitations in this class. However, the teaching assistants will periodically hold primers where we will bring you up to speed on various technologies that you may not be up to speed in, such as C. How many people have programmed in C before? And how many have not programmed in C before? A few, okay. Tools such as VTune. Who's used VTune before? Okay. Who has not used VTune? That's, yeah, okay, good. And a variety of, Pin, who's used Pin? Ooh, okay. Who has used Silk++? Okay, a couple people. Okay, so you see, we're going to have some primers to bring you up to speed in those kinds of things. We don't expect that you came in knowing any of those things particularly. Okay. Let's see, we're going to be using Stellar for our course management, and here's the URL. And you should make sure that you're registered as a member of 6172, because otherwise you're not going to get any announcements. We're going to do all of our administration through Stellar. So make sure that you're registered there. We will send out at the end of today, I think it is, we'll send out an announcement to the mailing list, the student mailing list. If you don't get something by the end of today, okay, so you wake up tomorrow morning, you have no email from the course staff, what that means is you should email us.
Well,
okay?
That mailing list would be the pre-registered ones.
That would be the pre-registered ones. And then that way we'll get all the people. So if you know you're not pre-registered, you can send us email before then. Okay? There are 2 one-hour quizzes given during class time. What's that? 1.5 hours. Oh, you're right. It's 1.5-hour quizzes. Okay. Yes, 2 1.5-hour quizzes. We'll correct that in the online version. Okay. Given during class time. Can somebody, by the way, correct this as we go along? Great. Okay. The dates are on the course calendar, which is available on Stellar. We've had mixed results with the ICS feed from Stellar, but you should be able, you're supposed to be able to download the calendar to your iPhone or, you know, other ICS-capable devices, but we were successful in downloading it, but all the times were screwed up. So, but anyway, hopefully maybe they'll allow that. But anyway, the calendar is there. The quizzes will generally be closed book and closed notes, but you will be permitted crib sheets. Okay, you know, one sheet that you summarize anything that you want to feel that you need to know. Generally, everything that we cover in here is fair game for the quizzes, including things that are in prerequisite courses. Okay, there's no final exam because we have a final project. This is a fast-moving class, and so if you get caught behind, is not a good sign, because it's really hard to work double hard to keep up in this class. Okay, you really have to keep on top of things. And so for that reason, and others, because it's really difficult for us, it's fast-moving for us as well, we generally cannot accept late projects. If you haven't been able to complete a project, you should just package up your partial solution and hand that in, and you'll get partial credit on it. Okay? Do not just say, oh, I'm not going to hand something in and expect to get it done later. If you do find yourself in an unusual situation, which you think there are some extenuating circumstances, like the aforementioned brain surgery or something, let us know in advance, okay? So if you're going to get in a car accident, it's really helpful if you tell us the day before, you know, so that we can plan. Okay. Obviously, can't always do that, but if it is something for which there's any reasonable expectation it should be done beforehand, you should let us know. And we may require for those kinds of exceptions some kind of confirmation from a dean or medical professional. So if that's the route that you're in, you can plan a little bit and make sure that those confirmations are on their way. The grading, this is essentially approximately how we're going to grade. As you can see, there's a bunch of content in the projects and a bunch in the quizzes. So, and then there's also a participation grade. And the participation is both in, we will have design reviews and such, and so that's part of the participation, as well as asking questions and such in class. And because we're video recording everything, we know exactly who's asking questions, unless you choose to sit outside the video zone. If, in addition, if there is a significant missing element to your work, it doesn't matter how well you did on the other things, you will receive a failing grade. So you must essentially do all the work, okay? If you do not get substantial credit on the final project or any other 2 assignments, for example, you can expect to receive a failing grade. It goes downhill very quickly. You know, if you're missing 1 assignment, generally don't expect to get higher than a C, for example. Okay, it goes downhill very, very quickly. Because that's what this is all about, is hands-on. What's permissible in this class? So it's your responsibility to satisfy both the letter and spirit of the rules. Okay, so if you have any questions, let us know. Here's what the rules are. Also, let me just say how Saman and I treat this. We have been involved in cheating incidents off and on over the years. I've been at MIT almost 30 years. Saman, you've been here 13 years, okay? So we've been here a long time, longer than you folks, okay? We've been through this a bunch of times. It's really a pain when somebody cheats. It robs me of a huge amount of my time that I could otherwise be spending on teaching and students and my own professional development, okay? However, we both take cheating incidents extremely seriously, and so we have this thing that is sometimes really inconvenient called integrity. You know, I'd rather, if I find somebody's cheating, just give you an F and not deal with it. Drat, you know. Instead, when somebody's cheating, I tend to want to take it to the Committee on Discipline, okay, where you face things like expulsion, et cetera. So I don't like to do that. It's very time-consuming for me, but I find it hard to just look the other way, because I sort of view the issue of integrity as protecting the vast majority of students who are obeying the rules. And so when a cheating incident occurs, you know, I sort of feel honor-bound to push it to its proper conclusion. So, so please don't cheat, okay? We will use a variety of means at our disposal, including technological ones, to detect cheating. Also, if you think that sharing your results with somebody else means that they're cheating and you're not, so in some cultures that's the way it's treated, okay? No. Okay, in this culture, and in particular the culture in this classroom, they're both equally guilty of academic dishonesty, whether you are the giver or the taker. Okay, equally, we treat that as equal offense. So here's the particular things. You may not share generally your solutions with people who are not in your group. So we will have a bunch of group projects, generally in pairs. And we'll treat them both, that includes both people in the class and people outside the class. Okay, so generally you keep things to yourself. Okay, when you're in a group, of course, you can share ideas within the group. Okay, but we expect that everybody's making a fair contribution. Okay, so you should be concerned if you are not holding up your end of your group participation. Okay, and we're going to ask you to sort of describe the contributions of the people in your group. Generally, the group, as I say, is 2. So it's basically saying, you know, what did you do? How did you divide up your project? What did you do? What did the other person do? You generally can't share it with anybody else. You can't copy or transcribe solutions from other places. The work you submit must be your own. Pretty straightforward. You may go out and use general conceptual material, such that you might get from a good textbook, okay, or from Wikipedia or someplace like that. That's perfectly fine. You know, the things that you would normally, resources you would normally have available. But you should, if you do use any material from an external source, you should properly cite it in in normal academic fashion. Okay, cite where it is so that somebody else can go and find and look to see what it is that you're citing. If you feel that you have made have transgressed in some way, let us know. It always goes way easier. I generally tend to be kind of a nice guy when somebody comes to me saying, oops, versus I hear from somewhere else or one of our tools detects something else, then I'm kind of cranky. Okay, so I'd rather, if you come to me, we can work something out generally. Most of your class time, out of class time, will spent completing 6 projects. And there's an outline of what the projects are. They're all fun projects. You can ask the TAs. The TAs will tell you how much fun they are, because they've generally not helped to design and built their own solutions to them. Some will be done in pairs, some individually. The final project can either be done in pairs or in threes, I think we said. What's that? Yes. We also have, we didn't put that in here. We also have a project 0, which will be available today after class. So you should go to Stellar and get project 0. Project 0 is not to be handed in. It's getting warmed up with all of the machines and tools that we'll be using in the class. We have been very fortunate to have very nice contributions from Dell and Intel of a new cluster facility that has 16 12-core machines. Okay, so and they're Core i7s, Intel Core i7 machines. Each chip has 6 cores, and there's 2 cores per machine, each with 48 gigabytes of memory. Okay, so these are kind of honking modern facility. Okay, so as I say, it's fun. Okay, it's fun when you do something on your laptop and then you go and you do it on one of these machines and it goes like this. Okay, it's really fun when these things go fast. Okay, so project 0 you should start on today, and it's basically the outline, the handout called Getting Started. It's available on Stellar, will be available on Stellar, and it will take you through getting access to these machines and so forth. In particular, in order to use these machines, you must have a CSAIL account. Who does not have a CSAIL account? Okay, so that is going to be the first thing you need to do before, because you've got to get that. So what you want to do is get registered for a CSAIL account by, and we give instructions in there. It's basically going to a web page pretty much as soon as you get out of the classroom, okay? Because you won't be able to start anything until you have the CSAIL account, okay? And hopefully we'll be able to give you access within a few hours after you register. Yeah, we're going to do, yeah, question?
What operating systems are the tools?
Linux. We'll be using Linux, okay? So there are a variety of ways that we describe for how you use these machines remotely. We have the Andrew file system, AFS, which you can use that you can edit things locally but have an SSH terminal window on the machine, which makes it very convenient. On the other hand, for some people, often some dorm rooms with poor connectivity, doing things by AFS may be too slow for you. Okay, but there are a variety of other ways that you can actually edit right on the machine, and there are a variety of ways of having a repository on your machine, because we'll be using Git as our versioning mechanism. So you'll be able to have it there and be able to make copies back on the other machine. So there are a variety of ways to work, and you're free to make the software run on your own laptops or workstations. The one thing I'll say is we will not support that. Okay, that we don't have the resources to support beyond using the machines in the machines that we actually provide. I think I've got to go faster here. So let's see. So software engineering. So research in programmer productivity has demonstrated that pair programming, where two programmers sit together, one at the keyboard and one looking on, okay, is actually faster than two programmers coding separately. Why do you suppose that is? Yeah?
You don't get stuck. Like the other person can tell you, like it's like when you're giving classes and you're writing on the blackboard, you get nervous, you don't know what you're doing. The person is looking from like beyond.
Yeah, you could be stuck. What else? Yeah, don't procrastinate. There you go. That's a good one. Don't procrastinate. Yeah, finding bugs. So the main one is finding bugs. Okay, that the person who's looking on finds bugs. In fact, I was just pair programming with Reed the other day, and we're trying to figure out why is this thing not working. And I say, gee, you know, it looks fine. It says, you know, next y equals x. And he says, no, next y is supposed to be y, equal y. And it's like, you know, we had both read over that code, but as soon as I spelled it out, I didn't even notice. But of course, him in hearing it says, oh, it's supposed to be x and y, not x and y. So anyway, that kind of thing you pick up very quickly, makes it very easy to debug. Likewise, regression testing demonstrably promotes fast code development. Okay? So this is where you build a battery of tests that includes tests for every mistake that you've ever made. Okay? And it can also be helpful to write unit tests where you test individual ones. And you should also use tools like the assert package. Okay? And some of these things will be taken through in Project Zero. The MIT posse. Okay, we have recruited senior software engineers in the region to share with you their valuable knowledge and experience. Okay? We call them Masters in the Practice of Software Systems Engineering, which has the great acronym MIT posse. Okay, these are people who are not being paid, and they're senior. Okay, they're doing this because they're volunteering, because they want to help. Okay? You have a lot to learn from these people, and we will have code and design reviews with these people, with your assigned master. You want to treat them nicely. Okay? They're not doing this so that some kid can say, you know, snotty-nosed kid can say, you know, I don't care about you. Okay? That's not what they're doing. They're there to help you get a good grade. Okay? And these are some really talented people who are very famous in their own areas of expertise. Okay? So give them the, you know, be gracious is the main thing I would say. Be gracious. Let's see. The assignments, I think we'll talk about, you can read about the assignments. Basically, generally what we're going to do is have a beta submission, okay, in which we're going to test everything, and we're going to also test your, we're also going to take all your tests. We're going to throw all the tests into a big pool and run everybody's tests against everybody's software. Okay, you will lose points if you fail some of the tests, assuming the tests are correct tests. You'll lose points if you have an incorrect test. You will lose points if somebody passes your test and they have a bug. Okay, you will get points if your test picks up something that very few other groups tested for. Okay? So you have to both submit code and submit tests, which is okay because you got to test your own stuff before you hand it in. Okay? But we're also going to be using it to test each other. After beta, we will have a design review with your master, design and code review with your master. Okay? And let me just say, the masters, they're not affecting your grade in any way. Okay? They do give us reports about what happened in their meeting, but they have no bearing on the grade. They're just there to help. Okay? So you don't have to view them as you know, they're not part of the course staff. If you want to get angry at somebody about how things are done, get angry at Saman and me. Okay? Don't get angry at them. The final submission is generally due a couple weeks after the beta, and it's after you've gotten feedback on your design, feedback on things. You can, you know, we'll give you the whole battery of everybody's regression tests so you can test out your code against everybody else's regression tests and use that. And then generally, the scoring is such that people who get fast code get high marks. People who get slow codes get more marks. Okay. If you need help, let it. Speed is fun. You know, enjoy the class. Yeah, question.
In terms of bug testing, I'm thinking of bugs like, I don't know, array index out of boundaries or something like that. If you happen to not have made a bug in your own program and therefore do not test for it, would that count against you for final testing?
If somebody else, so you have to view your beta test. You have to view your beta test as testing other people's code also.
But,
Okay?
but if you create a test that find bugs in somebody's program, and if you are if very few people wrote that test, then you will get points. So you don't have to test for the world, everything. If you fail somebody's test but not yours, you will be deducted points. If your test find other people's bugs, you will gain points for that. But on the other hand, you don't have to test for. Yeah, what you said, I think if you don't have to go and test for every possible condition in there. The positive, negative side is if you miss something, you will deduct points. Positive side is if your test finds somebody else's problem bugs, you'll get points for it. We'll go into detail exactly how it went. Another thing we did last year, which was very, kind of interesting. I think there were mixed. Some people really like it, some people are not that happy. Is a little bit of competitive grading. So here, what we are doing is not the full grade, small part of the grade. What you do is, when you first submit your beta, we run performance tests of everybody. And of course, one of you is going to get the fastest code for that. And at that point, we are going to say, okay, this is the fastest code. And how off everybody else with that code. And the person who gets fastest code will get that, for that part of the grade, get the full points. And everybody else will get a partial part of the points. However, you get a chance in your final submission to basically improve your code. If you do better than the last time's best code, you won't get any more additional points, because then we don't want to keep arms race. So you at least have to match the previous times. You then need to get full points. And so you get a chance to see how you stand against your peers, and get a chance to actually come and match with your peers. So first time we said, okay, it's the faction of your performance against the performance of the best code. The problem was there were a couple of code that got 1000x performance improvement and everybody else got 10x. So you got like 0.25 grade. That didn't help. So now we're actually doing a log scale. So we'll get the fraction and we'll take the log of that, and so there'll be a little bit more equality here. But so you will know how worse off you are, and you get a chance to come match up, because this is very important, because a lot of times there might be a crucial thing that you missed. And instead of trying to be, got you in this class, we are trying to give you a chance to actually learn. So if you missed it, okay, you missed it first time, but you get the second chance to come and fix it and see whether you can do. And of course, if you do better than the best grade, there are bragging rights, but you don't get extra points. So with that, let me, where are we? Okay, so again, as Charles pointed out, I'm pretty excited about this class. This is a really fun class. Unfortunately, I'm a little bit under the weather, so I'm going to sit down here, and if I doesn't sound that enthusiastic, hopefully I'll get enthusiastic later. And that's one reason we asked you to come forward, because we don't have to come here and shout. So hopefully people in the back can hear. If you don't, still there are some seats in the front. You can move forward. So for the rest of the class, what we want to do is go through an example and look at why performance matter. Okay, and for that I selected MatrixMultiply, and I think your project 0, you're going to also play with MatrixMultiply, and I think that will be really you'll get a kind of feel for what kind of things can happen, and how much of a room you have in doing well in here. And on the same time, when I go through this, you'll get a feel for what's the process that you might be following through the class, and what kind of things, because when you're programming, after taking bunch of programming class, probably you have a methodology set up in your mind how to go about doing that. And the same thing after this class, we want you to have a methodology of going through and improving performance. And this is the basically a little bit of a contrived example, but you'll get a feel. So what's matrix multiply? It's a very fundamental operation for many computations. So you want to produce matrix A by multiply matrix B and C. And so you want to calculate each value in here to take a row of B and a column of C, and you get each element of A, and you do that for every element of A. Okay? And this is the possible simplest code you can write in a language like C, 3 loop nest and this matrix multiply. Okay? So far things should be pretty simple. And so what I did was I looked at matrix multiply and said, look, you have taken a software engineering class, you have thought about object oriented programming, lot of nice techniques to build very useful portable software, and let's try to write matrix multiply with some of those concepts. So the first thing I want to do is matrix multiply write object oriented using immutable classes, and that in fact I want matrix class to represent both integers and doubles. So here's my class structure in here, and actually I'm going to show you a bunch of code now. Next couple of slides, I'm not expecting you to follow everything instantaneously. I'm going to go through it somewhat faster, but you'll have the slides. So I also expect you to perhaps in some free time to go and look at some of these slides, get a little bit of better feel for what happened. So here's what matrix multiply does. I have a value class that figure out whether matrix type, and if it is integer, I keep integer. If it's a double, I keep a double. And here basically do this value in here, and then I have a matrix class. Basically, given a matrix type and a matrix, it can create a matrix here. This basically create your matrix in here by first creating a bunch of rows here, then instantiating each row in here, whether it's an integer or double depending on the type given. And then of course there are other things in matrix basically in here, and you can update a matrix. This is going to be a little bit interesting. I will get a little bit here, because what I am doing is I am doing immutable types. That means I can't change anything in the matrix. If you are updating, you have to create a new matrix. So how do you go about, I will go show a little bit how to go about doing that. And then there's this row class. Okay, I am going through this fast because this is not that important. If you get a chance to go through this and get a feel for what I am doing, but idea is doing this very software engineering way of implementing a matrix multiply. So and then here's my matrix multiply in here. That what I do is I am updating each of these matrix by getting a value of B and C and adding it to A and updating A again in here. So when I ran matrix multiply by 1024 by 1024 matrix, this is the time I got. Actually, it took a long time, in fact. Okay, and the key thing is the performance good. That's the first question to ask, because you run something, you get a result. When the result is correct, okay, great, you get the correct result. But how did you do? And this is sometimes a very hard thing. To know that you have a problem is itself a huge win, that you actually figure out you have a problem. And what I am going to do is go through a little bit of a calculation to see how it did. It took about 5 hours to do this matrix multiply, and that doesn't look right already in here. So if you think about matrix multiply, it's an n cube operation basically. What matrix multiply is doing. Okay, that's the algorithmic class. If you look at Charles's book, that's what it would say. It's an n cube operation. So this is number of operations you want to do. Okay. And for each matrix operation, you want to do 3 index operators, add and a multiply and a check, probably 6 ops to do basically. Okay, and that means I need to do this many operations. Basically, as, you can think about like machine operations to do basically, because you have to read 3 values, update 1, do a multiply and add, and do a branch. Okay. And if I look at that with my hours, I am doing this many operations per second. It looks high, big number. But my machine actually, this run on my somewhat old PC, it runs even much faster. So if you think about it, I am taking about 8,300 cycles to do any kind of a machine operation. This does not look right. Okay. So, at this point, this is what I would call a back of the envelope calculation. Okay, I have not proven anything, this will not work well in a theory class, but if you can just jot down a couple of these things, you can get a feel for where you stand very fast. And then you realize, okay, I am a couple of orders of magnitude off here on what best I could do, and that should give you a feel for what is going on. So, okay, so what is going on here? How can we improve performance, because we know we have a problem. So, what we can do is we can look deeply into the program execution, and at some point say, okay, this program runs slow, now we figure out where's time spent. So, we can figure out time spent basically things like by method, which method you spend most of the time running, sometimes by line, and we will learn bunch of profiling tools that will give you this feel. So, instead of when you have million lines of code looking at every line in there, you can very fast converge onto the culprits where most of the time being spent, and that is a very easy way of triaging your problem. And you look at things like time spent, cumulative time spent within that, and everything called underneath, number of invocations of that function, and a lot of times you have a feel for what it should be. And when you look at this, if it does not look right, you say, wait a minute, this goes against my intuition, perhaps there is a problem. So, what you can do is by doing this, you can identify hotspots. Basically, if 90% of the time is in one routine, that is what you want to fix. And hopefully, if that routine is doing something too slow, then you can actually get good performance in here. So, here is the profile I ran for MatrixMultiply, and interestingly what I found was most of the time spent in basically creating doubles. Okay, number of calls, time spent here, this much time was spending basically creating new values in here. Okay, this initializing double in here. Okay. And so I am doing matrix multiply, why should I be initializing values? So, this is the issue, and I have the most number of calls to that too. So we can go look at and say, hey, there should seem to be a problem here. So, the problem here was kind of obvious. What happened was I did use immutable class. So, this is my matrix representation. I have a bunch of pointers pointing to each row, and now assume I want to update this element. And of course, I can't modify the entire thing, it is immutable. So, what I had to do is create a copy that update, and then of course, I had to create a new matrix. I do not have to copy everybody else because these guys were not changed. So, I can place a pointer to these things and create this new matrix that point to this thing. Okay. And then if you think about what is going on, in fact, and this is my new matrix, after I do that, I am doing 2n copies for each update. Because what I had to do is I had to copy this entire row up to get that, and I have to create this entire index again for each point into each row. So, just to update one element, I am creating 2n copies. So, what that means is now our n cube matrix multiply end up being n to the power 4 algorithm. Okay. So, suddenly you realize, wait a minute, I am doing something bad in here. I am actually took n cube algorithm, and the way I solve it becomes n to the power 4 because I am making all these copies in here. So, this is a bad thing to do, of course, and copying is very costly because you are making duplicates in here, and of course, you are creating huge amount of garbage because you are just copying and leaving the previous value for garbage collection. So, garbage collectors coming up all the time and huge memory footprint. So, this is no good. And can we do better? Hopefully, we can. So, the next thing we did was, okay, just get rid of this immutable types. Okay, that seemed to be a loose case here. And then I actually I will go fast over the code. So, if you are interested, you can go look at the code in here. So, here what we did was just still we have the issues like object oriented and ability to represent both integers and doubles. So, what that means is each matrix can be the integer matrix or a double matrix. So, this is why we are instantiating with the integers or double in here, and so we do that. And how much you think this can improve performance so far doing that? In fact, this was pretty nice. I actually got a 219x performance improvement because I went from n to the power 4 algorithm to n to the power 3 algorithm. So here's an interesting algorithm is change we did, and we have pretty nice performance improvement. Okay. So if I look at this now, what I find is I am spending lot of time, method time I am doing matrix multiply, that's good, but I am spending all this time doing get double and get methods. Okay. I am trying to do matrix multiply. Why am I spending all this time trying to do get double and get? What I found was issue is the method call overhead. Right now what happened is matrix row has two different matrix types, the integer row and double row. So every time I want to get a row, I don't know whether I have integer row or double row. I have to go do a lookup to figure out what my type is. Am I working with the integer matrix or a matrix with doubles? And this is what we call dynamic dispatch. So instead of knowing exactly the method where to go, I had to actually look up, okay, which method I am supposed to go. I have to do that, since if the matrix was integer, I might have to call a different method. That matrix is double, I have to check that, and then that call become, instead of a direct call, become an indirect branch. I have to check that and basically branch on that. And these indirect branches are costly, because what that means is I don't know where I am going until I do that test. So normal machine, we'll got into details on pipelines and stuff as we go on. What that means is normally a machine can have lot of instructions in flight. So that means as I have to know a lot more information to get instructions going, but here until you resolve the instructions you can't do the next one. So it's called a basically pipeline stall. So instead of having hundreds of instructions going, I basically suddenly I can't do anything until previous instruction is done. So the machine slows down a lot, and because of this. So normally what we can do is keep fetching next instructions. Here we have to fetch, test. When the test result is available, then that's when you can fetch the next instruction. Okay, okay, let me go through that file. So direct branch means target address is known, you can fetch ahead of the target. So if I know where I am going, even if I don't get there, I can fetch ahead of the target. I can go start fetching what happens next ahead, basically in direct branch. Sometimes you can even fetch both directions, or the direction you might always go might get fetched by the architecture. We will talk about a lot of architecture details in future lectures. Indirect branch means until I calculate the address, I have no idea where I am going. That address is only calculated, and because of that hardware slows down like crazy. So this seems to be not a bad, not a good thing to have these integers and doubles. Instead of having one nice class, which was software engineering wise might be nice, I just basically create just a double class. Yeah, it's all matrices are doubles. If I want integers, I will just rewrite my matrix class or copy and replace. Okay, and now my matrix class become much more simpler. This is what I got, and this is my row in here, and voila, minute I do that, I basically have another about 2.4x performance improvement, because now I don't have to keep doing that. Okay, and altogether now I have improved my performance by about 500x here. Okay, and for ops per cycle we have gone down from 8000 to 38 to 16. Okay, so we can do still better. And now we look at again my profile data. And now what I see is, okay, I am spending a lot of time in matrix multiply, that's get, but also I am spending time in this matrix get method. I am trying to get each basically row and data elements of the matrix, and that's because, okay, what am I doing? So here's the kind of summary of these things. I am going to just skip that one because I gave you the short thing. So the problem with this object orientedness is, I have now each rows represented separately, nice objects. These objects are all over the memory, and in fact if I want to get to my row, I have to do a pointer chase to go get that. It's not contiguous in memory, and to get to every row I have to actually go through this pointer index in here. Okay, you know, matrices are one nice simple objects. So we can say, okay, wait a minute, this method call overhead actually keep dominating, and because I have done this nice object oriented thing here, so I can get rid of the object oriented part here. Okay, and said, okay, get rid of the objects, and I write this nice loop of 3-leaf div, and I have 2-dimension matrices in here, and voila, I got another 2.2x performance improvement in here. Okay, now I am down to about 7 cycles for each operation in here. That's good. Okay. So what can we do here? So we did all these things in Java because it's supposed to be a nice language, but Java has a lot of overhead. It's like you do memory bound checks, you have to do this byte out interpreter and stuff like that. On the other hand, C can run much faster. You don't have to do any kind of memory bound checks. The compilation happened before you run, so it's not part of your cost of doing anything. And also this code looks very much like C. You can just almost cut and paste. And if you know C syntax, changing this to C is just changing few lines. And I did that, and this is basically the C code in here. This is the matrix multiply. This is the kind of allocation in here. C can be a little bit painful to allocate. This is my matrix multiply. It will almost look similar. And I got 2.1x just by going from Java to C. This I was surprised because that piece of Java code looked very much close to C. But just by doing that, I actually got another 2.1x performance gain. Now we go, actually now this is kind of the high level stuff. Now we have to go to nitty gritty details in the hardware. So in modern hardware, there's these things called performance counters that the hardware Intel and AMD gives us, that we can look at what's happening inside hardware. We can get a feel for what happens inside hardware. And there are things called CPI, which called clock cycles per instruction. So that means if the instructions are running very slow, you will have multiple clock cycles for instructions. That means instructions are stalling, something is wrong. Cache misses. So data will go lock details into caches and stuff like that. If data is supposed to be in cache and have cache hits all the time, but if you are getting cache misses, something is wrong. Accesses are not good. And then also the instructions retired. That means how many instructions are being executed and retired. If you are doing too much work, the number of instructions retired will go high in here. This kind of gives you a feel how many work being done. And so if you look at this one, I have a CPI of 4. That means I am running almost, for every instruction need about almost close to 5 clock cycles, which is not good. I have pretty high cache miss rate too, L1 cache miss rate and some L2 cache miss rate. This says how many instructions are in what they call a vector instruction form, called SSE instructions. And here's the number of instructions got retired. So we just use that a baseline case. And so one thing I can look at was this cache miss rate seem to be pretty darn high. What might be happening here? So if you look at matrix multiply, so I have matrix A in here and matrix B. What happened is to calculate this value in matrix in here, I am going to get this value. I'm basically I'm going to go through this row in here, and I'm going through column in here. Problem with the column is it's all over the cache. Okay, this is your linear memory. So this is because this is your 2-dimensional, but inside your hardware there's no 2-dimensional memory. You have a linear memory. So this is your linear memory. This is how the memory look like. And this is how the memory look like. So each row and column is in these areas, but here to calculate this value, this is nice. I go through memory that is contiguous, but see, I am jumping all over my memory. And jumping on memory is not that great cache behavior. And contiguous can do much better, because what you do is when you get a cache, you get a cache line that has more than one word. So in here what you are doing is you are getting large cache lines and only using one word before you go to the next one. So that's not great in cache behavior. So what you can do is you can make this memory contiguous. So so what you can do is in matrix multiply normally n to the cube computation, n to the squared data. So to help on n to the cube, it's okay to do some n to the squared processing. That means you can do a data transpose before you start matrix multiply, do some pre-processing. So this will also come in handy. A lot of these problems you do, you see like, wait a minute, can I do a pre-process that's cheaper, that will really improve my main processing. This is a theme that comes again and again. And then we can get this n to the cube running faster. Since this n to the cube is much larger than n to the squared, you can amortize the cost of doing that. And basically to get that, we can transpose our matrix doing n to the squared operations, and then our n to the cube might run much faster. And in fact what I have done here is do the transpose of this matrix, and now we run this one, and then everything will be contiguous in memory, and voila, I got another 3.4x performance improvement. Now I am running almost about 1 cycles per op, so which is really nice. But modern superscalers actually can do better, so we can actually end up being even better. So let's see. So we are doing that. So here's the interesting thing. Now I look at my transpose part. So if you look at that, number of retired instructions is more or less the same. Number of SSE instruction more or less the same. I have a 2x improvement in my L1 cache miss rate, but more than that I have a 5x improvement in the CPI. That means is my instructions are stalling lot less now than before. Okay? So this is where I got all my performance insight, because my instructions are running much faster. Okay? So by looking at data, this is the kind of things you will learn during the class, then you can get a feel for what actually is happening and why you are getting that. You can go do more in the cache, in memory system. So the memory system, if you look at caches, what they are doing is we have very small amount of memory called caches that have very fast access, and you have large amount of memory that have sitting out there that has slow access. So what you want to give user feel is they have lot of memory, everything is very fast access. So hardware does lot of crazy things to give you the illusion that you have very fast memory and you have huge amount of that. Of course that's not true, because you have these caches, and what happens is if you do things wrong, things get slow down. So in the cache system, you have a cache hierarchy like that. You have each multi-core going to its own L1 cache, that goes to L2 cache, which go to L3 cache, which goes to the main memory system. And you want all the data to be here. If that's the case, strings run very fast. If not, you have to go here, it will be much slow, here even slower, here very slow. So the key thing is to get the data as much as possible here. So here's the kind of cycles, basically one cycle to get here 3 cycles. If you go to L2 to L3, you have to do 14 cycles miss penalty. If you go to L3 to main memory, you might sometimes get hundreds of cycles delay in here, so it's very costly. So the caches are very temperamental beasts. They work beautifully, but when they don't work, things go really haywire. So you have to, lot of times that's why you look, if there's a performance issue, you look at the cache miss rate and say, aha, the caches are not behaving, and can I help it here? So the interesting way to look at that is how much data I touch. This graphics didn't show up, but okay, let me explain. So if you do matrix multiply, I am trying to calculate one value in here. Okay, why am I? Okay, so this is one value. I have to calculate row and a column. Okay. This slide got screwed up a little bit, so just look at the first this calculating row bar. So if I want to calculate a row of values here, what I have to do is I have to get this row in B, and I have to use entire C to calculate one row of A. That means I have touched this much data items just to get one row of A. So that means I am calculating 1024 values of A. I am touching this much data items to get that. On the other hand, if I do block matrix multiply, that means I calculate basically a block in here. This block also 32 by 32 has 1024 elements in here. But I only need a block here and block here. Voila, I only have looked at 25,000 elements. I got the same number of output calculated. Okay? But I have only touched much less elements altogether to calculate that. Do you see that? And a nice thing is, if this thing fits in the cache, I am much better than this might not fit in the cache. So I can calculate blocks in matrix multiply by looking at lot less number of data that has a good chance in fitting in cache, and of course when you calculate you make sure it fits in cache, than trying to just calculate row by row. Okay? So one thing you can do is, this is lot of common things we do. There's many ways to get same results. You can change the execution order, you can change algorithm, you can change data structures, and some of them actually might do better than the other. And here we can actually say we can do the execution order change and make sure with only looking at small amount of data you get the same number of data calculated. And of course sometimes you have to be careful, because if you do things in different order you might not get the exact same results. So if you are a numerical analyst, you say, okay, of course, if you are doing A plus B plus C, what order you do will make a difference. It is. And so if you are really careful, you can't do too many things, but most times you can do some of these things. You can, and in fact, in our final thing, we might say, final project, we will give you something that you can change the algorithm as long as the outcome of the image is the same. If you look at the image, if the image outcome is the same, you can go change things. So a lot of times you have this, you might have a lot of freedom to change the amount of errors you get, the precision, and in fact, doing that you can actually get a lot of good performance. So in here we are not trying to change matrix multiply, of course, but we are going to change the way order of operations being done. So some people say you can't do that, it will make matrix multiply different, but most cases it's okay. So what we have done is done what we call block matrix multiply. So instead of calculating rows, you calculate blocks at a time. So calculating each block, you only need few amount of data. So this is block matrix multiply. And voila, by doing block matrix multiply, I got even 1.7x performance gain from there. Now it's very interesting. Now each clock cycle, I am doing 2 operations. So my superscale is finally coming to being. So every clock cycle, I am doing multiple operations here. So this is very interesting, the number here. So now when you look at what happens here, I am actually executing a little bit more instructions here. Why? Because I did blocks matrix multiply. That means I am doing a little more overhead in here. I have more loops in here. My inner loops are small, so I am doing more instructions to do execute there. So I am doing more instructions, but I have a huge cache performance gain. Okay, my cache miss rate now gone down to very, very little, 0.02%, and I have 8x improvement in cache, and that means I got a 3x improvement in my CPI in here. Okay. That's very nice. That means even though I am doing a little bit more work, my cache behavior really, really helped me in here. Okay, so this kind of says why I am getting this performance gain. So what else can we do? We can go look at and trying to do a lot more crazy optimizations, because if you look at a modern Intel, they have this thing called vector instructions. We'll get a little bit more detail into that later. And what we can do sometimes is you can nudge the compiler to take advantage of these instructions. Of course, if nothing helps, you can actually go and write to assembly language, but hey, I don't want you guys to write assembly code, at least in this class, even though you can get really good performance sometimes. But you can kind of give enough hints to the compiler and pray and kind of do, because there's no nice way on these things, and hopefully the compiler will do the right thing. And so in here, we can play with a lot of times compiler flags, and this is not exact science. You keep trying those things, and sometimes you can even get information back and say, okay, what did the compiler do? It might say, it might give you some good hints and say, I couldn't do something because of this part of the code. And worst come to worst, you can actually generate assembly and stare at it. And sometimes in this class you might actually want to stare at the assembly and see what goes on in here. And so here's the assembly for here, and this is my loop body in here. And then what I can see, I'm not going to go through that, everything is converted into SSE instructions. At least I know what SSE instructions mean. So this seemed to be doing well, so I'm happy. And in fact, I'm really happy because now I got a 2.8x improvement by doing this. Okay, now I am actually doing each clock cycle about five of my operations. So I'm going really fast in here. So now, incidentally, I have I'm running my program about 30,000x faster than when I started. So if you haven't noticed, these things slowly add up in here. Okay, and now if you look at what's going on here, this is very interesting. What I have done is actually my each instruction is now CPI is gone down. That means each instruction is running slower because I am doing these SSE instructions. And in fact, my cache miss rate has also gone up. But I am doing a lot less instructions because SSE means in one instructions I am doing a vector. So I am actually getting 4 operations done in one instruction. So number of instructions I execute has drastically gone down. So even though my instructions are running a little bit slower, I can basically amortize that and I get good performance in here. And of course, this one says, okay, now 88% of the instructions are SSE. So I have actually mapped most of the things to run on vector mode in here. And of course, you can keep doing more and more and more. And there are these, for things like matrix multiplies, there are people who spend their entire lifetime trying to run it faster. And they have libraries like that. And there's a thing called a BLAST library. and there's thing called Intel Math kernel. And so they have done a lot more other things like prefetching, getting everything right. And so here what I do is basically call their library, don't do anything myself, and that library will do it for me. And in fact, that library itself gave me another 2.7x performance gain in there. Now I am actually doing 11 instructions every clock cycle, and by doing that. And if I look at carefully, what they have done is they are also very into SSE heavy. So they are running almost same amount of instructions, but they managed to actually get again a better miss rate. They probably figure out some stuff in here, things like prefetching instructions, and that means they actually brought down the CPI back to where it was before, and that's what they gave that performance for them. And finally, we are going a little bit of parallel execution. And so as you know, multi-cores are here, and you are actually going to have these 12-core machines, which are really nice, fastest possible machines you can get your hands on these days, and it's kind of fun to work with them. And we can basically get concurrency of parallel performance, and large part of this class at the end is trying to get good parallel performance. But there are a lot of issues with parallelism. I'll go a couple of issues now. Of course, when we get to that part, we will go in detail. One thing is called Amdahl's law. Because if you are trying to run something parallel, you can't run everything parallel. You have when you start something, there's part of the code that basically starts the computation, and then there will be parts you can run parallel, and then other parts you have to also wind down, measure, things like that. So what Amdahl's law says is, even if you have infinite number of processors, the maximum speed up you can get is this. This is the part of the code that are sequential and process codes are parallel. That means if you have only 90% of the code can be parallelized, the maximum speed up you can get is 10, even if you have infinite number of processors. So 99% of the code is parallel, maximum speed up you can get is 100. So this is very interesting, because even if you have huge big machines, if your code has certain amount of sequential part, there's a limit of what you can do. There's also a thing called load balancing. That means when you get parallel, what you're assuming is all processors are busy all the time. That's very hard to achieve. Sometimes some processors are busy, sometimes others are not, sometimes some things finish early. So if that happens, even though you have parallel, so you might not get really good performance in here. And then of course there's thing called granularity of parallelism. Normally what happens in a program, you run sequential part, you run parallel part, you run sequential parallel part. To start parallelism is a big task. You have to tell all the other processes, okay, look, you guys have some work, go do that and finish that and come back. And that itself is very expensive. And the work you give is very small. You give the work, the startup and tear down cost of parallelism itself might be too much than the speed up you get. In fact, you can make programs parallel and slow them down really drastically. So you have to be very careful in that, because you can say, oh, I'm running parallel, but it's running slow. Why? Because you might have a granularity issue. Because we are giving so little work that even though you are getting a lot of parallels, you might not get that much performance. In fact, so if you look at MatrixMultiply, what happens here is you can divide the matrix into two different parts in here and calculate as two different matrix multiplies, each in a different core or different process. So in here I can make it 2 or whatever in matrix multiplies to do that. So this nicely parallelized, no big issue in here. And when I parallelize, I got another 3.5x performance improvement. Of course, this is I could have gotten more here, but since I didn't, because I had to start here, since I didn't want to wait for a week for this to finish, I had to come up with a smaller matrix size. But now when I get here, this is so fast, my granularity is too small. So that's why I didn't get 8, because this was 8-core machine, I didn't get 8x, because the minute I get parallelism, it's over, because it's running so fast in here. Okay. Now at this point, using 8 cores, I am actually getting 36. So this is not that interesting, because this is not running on 1 core. I am actually getting every clock cycle, I am trying to get 36 operations done. So the interesting thing to follow in here is that this example might be somewhat contrived, because I started with like this immutable type matrix multiply. Hopefully even your colleagues who haven't taken this class probably won't go that far, but even if you start somewhere here, still there's a huge gain to be made. So to put this in perspective, okay, so if you look at here, even if I start here somewhere around in C, I already gone 131x performance improvement. That's huge. Okay, so that means we are not in this class, we are not talking about small things, and in fact this is why I had to go log scale in doing absolute grades, because we had people who figured out exactly how in some problems change data structures, change execution ordering, do some really cool things, get 1000x performance improvement, and there are other people who did little bit things and got 2x improvement. So the fact that what you can do the best here can be really, really high. Okay, so that's why we actually start giving you the second chance to also go basically see if you missed a critical point, to go back and learn that. So to put this in perspective, so in summary, what we have done is MatrixMultiply might be exception. Every time you go, you might not get that much, but in here, going from this very software engineered, nice high level approach to blast parallel, I got 296,000 times performance improvement. This is huge. If you put this in perspective, if you look at miles per gallon between these two, a super tanker and this scooter, is only 14,000x basically. So what that means is you have to have 20 super tankers to basically match this much improvement. So if somebody can tell you, look, I can get a super tanker run at the same miles per gallon as your scooter, that would be revolutionary. Okay, but you can do something similar in your computer. And in fact, if you look at these large data centers, the computers are actually burning lot of energy, lot of cost, and in fact, if you can reduce that, that can have impact. So what you get out of this class is to think through these programs this way. You learn about correctness before things like 6170. Hopefully you are good at writing correct programs, but that's not good enough in a lot of times. And how do you think about programs, how to make it run faster? There are multiple necessary. So for example, in here it's basically direct energy. So if you get data center to burn use 10% less energy, that's huge. And for example, if you look at today's supercomputing centers, they spend about $10 million a year on energy just for the power grid. So if you can say I'm saving 10%, that much huge. Other thing, one thing Charles says a lot of times is what performance gives you is currency. Because performance itself might not be that directly useful, but it gives you currency to buy something else. What it is? So assume you have a nice application. Your GUI is doing okay. It's up to the point that people don't feel stalled. But if you want to do something addition, if you want to add a feature, okay, you don't want to slow down the program too much because your users are going to complain. So what performance gives you is, if you improve the performance, it gives you currency, the ability to buy some additional features into your system. Or you have a system that you created a startup and you created this nice server somewhere. Suddenly it became very popular and million people want to use your software. Okay, and the software might not be ready to do that. It might just crash and burn, or you might have to pay a lot for money for Amazon for all the cycles. So by actually making programs fast, you can make it scalable, you can make it efficient. So this gives you the ability, this currency, to go do a lot more other interesting things to your software, because now you can run it faster. It gives you this margin to play with. So in this class, we are going to learn a lot about these things. We are going to learn about architecture, looking at the architectural issues, how to identify something is wrong. We are going to look at algorithmic issues in here, how to look at things. We are looking at architectural things like memory systems, parallelism, and also we will talk about all the tools. So you will actually know something is gone wrong, because today you run a program, it runs correctly. Is it good enough or not? How do you identify that? That's I think the very interesting place to start. So that's all I have today, and make sure you get project 0 and especially people who haven't done C, we will, Charles, are we going to do a C remediation? We did last time, isn't it? Okay, guys, one more thing. Last year we did a evening C remediation class. So if you know Java, if you want to know C, we will send out a time with TAs that will give you kind of a 1 hour crash course into C in there, and we will send information. So this class moves very fast. Get on with Project Zero, and see you next week.